It's now my great pleasure to introduce Professor Anthony Powell, our first speaker. Professor Powell graduated in chemistry from the University of Oxford, and after postdoctoral work at the same university, joined Heriot University in Edinburgh as a lecturer in inorganic chemistry, where he was subsequently promoted to reader and to professor. He was the founding director of the University Center of Advanced Energy Storage and Recovery, and in 2013, he joined the University of Reading as head of department in chemistry. Later, he held the position of director of research in chemical science. Professor Powell's research interests in solid-state materials chemistry focus on functional material with technologically useful properties. Major themes include materials for energy application, especially thermoelectric materials, novel electronic and magnetic materials, low-dimensional solids, and porous semiconductors. Many of his investigations are underpinned by neutron scattering at central facilities, for example, at ICES Neutron and Muon Source in UK. Last but not least, he co-chairs the UK Thermoelectric Network. So, dear Anthony, thank you for accepting our invitation and taking time out to participate in this workshop.
Thank you, Jesus, and thank you very much indeed for this invitation, and also to those people who've been working behind the scenes over the last half hour to try to resolve some of the technical problems that we've been experiencing. So what I'd like to do today is, because I think thermoelectric materials are maybe a little bit less familiar than some other categories of energy materials, I thought I'd start with a little bit of an overview of thermoelectric materials and then draw on some examples, which will be mainly from our own research. So a thermoelectric device is essentially shown down on the bottom here. This array of essentially N and P type semiconductors that are connected electrically in series and thermally in parallel. So this is a commercial device that can be picked up from RS Components or some other supplier. And essentially, if you apply a temperature gradient across that device, so from top to bottom, for instance, then what happens is both the holes and the electrons, so it's an array of N and P type semiconductors, the holes and the electrons carry heat away, and then it's rejected at a heat sink, and in doing so, it creates an electrical current within that device, that the holes and the electrons moving from one end of the semiconductor to the other create a potential difference. It can also be used in reverse, whereby you apply an electrical current to it or apply a voltage to it, and that then causes the holes and electrons to act as a heat pump, and it can act as a refrigeration. I'm going to talk principally about energy generation today. I do have a video here, but I think in the practice runs that we did earlier in the week, the video didn't really work properly, so I should probably skip that rather than risk pushing the technology to its limit. Now, talk a little bit about application areas. So as I say, if we want to generate electrical power from that thermoelectric device, then we have to put a temperature difference, a temperature gradient across the device. But it really doesn't matter where that thermal energy comes from. So it can come from industry, for instance. Steel, cement, and glass are two of the biggest areas in industry where there's a significant amount of waste heat. Transportation's another area, and certainly we've been working on materials for automotive type applications. Aerospace, these materials already used in deep space probes, for example, where there's not enough solar energy to provide electrical power, but there are also potential applications in non-safety critical areas in aircraft. And then there are the sort of more niche areas of application, which include things like wearable electronics. So we've been working, for instance, recently on a project which tries to use body heat here. There's also potential applications in terms of combining them with photovoltaic devices in order to extract some of the thermal energy that's impinging on these solar panels, for example. So in essence, I guess the message is that any source of waste heat can be turned into electricity using a thermoelectric device. Now, we'll see a lot in this talk, and if you look at the thermoelectric literature, this parameter ZT, ZT is kind of it's called a figure of merit. It's an indicator of performance. So it's a useful indicator in some respects. I sometimes think that people get a little bit too hung up on the value of ZT, but it's a useful indicator to compare across materials the level of performance. And it depends on the fundamental materials parameters, the Seebeck coefficient, the electrical conductivity, and then the thermal conductivity, which has got two components to it. It's got that due to the charge carriers, the kappa E as it's indicated here, and it's got a component due to the vibrational modes of the solid, the phonon component, which I've labeled here as KL for K lattice, the kappa L, kappa lattice for the thermal conductivity due to the phonon transport. The problem in terms of designing a material that has a high value of ZT is that these parameters of the Seebeck coefficient, the electrical conductivity, and the electrical part of the thermal conductivity are all interrelated. So for instance, if we were to plot these parameters as a function of the charge carrier concentration along the x-axis, we'd find that the materials that have a very high value of the Seebeck coefficient are generally insulators or non-metallic materials with a fairly low charge carrier concentration. And of course, what that means is that they have a very low electrical conductivity. Conversely, if we go to materials which have a high electrical conductivity with a high charge carrier concentration, they've got a low Seebeck coefficient. So there's a trade-off in terms of the numerator of this expression. So this S squared sigma term is known as the power factor, and that sort of peaks somewhere in the middle here, which corresponds to heavily doped semiconductors. There's also as I say, the thermal conductivity element of that, which is an issue, is that whilst the lattice part of the thermal conductivity is largely independent of the carrier concentration, the electronic part will of course get higher the higher the electrical conductivity, and in fact they are directly related to each other through something called the Wiedemann-Franz law. So to try to encapsulate the problem, it's a multi-parameter problem really, but to try to encapsulate it in one statement, I would say that one of the problems with the thermoelectric is that we need something that gives us the conduction of electricity that's like a metal and the conduction of heat like an insulator, so in the same material, and that's a major challenge. The only current commercial material is this one, which is bismuth telluride. This is a layered structure, so it's these blocks of octahedra that, so this is like the metal dichalcogenide structure, but taking pairs of them which share common faces. So we have these paired blocks and then a van der Waals gap and then another block of bismuth telluride. So it's a layered structure. That in itself can introduce some problems because it means that the properties are generally very anisotropic. And often in terms of powder consolidation, where we're pressing an ingot, we need to be able to cut that ingot in particular ways in order to measure the transport properties, both parallel and perpendicular to the pressing direction, because the anisotropic structure gives us an anisotropy in terms of properties. The nice thing about bismuth telluride is that it's possible to make chemically compatible N and P type variants. So if you remember, the thermoelectric device has both N and P type semiconductors. So we could make both N and P type versions of it through suitable doping. It depends a little bit on how it's fabricated and manufactured, but typically the ZT of bismuth telluride is between about 1 and 1.3 at 400 Kelvin. So that sort of sets a benchmark at these kinds of temperatures in terms of performance. And that's why, as I say, bismuth telluride is really the only commercially available material currently. And the reason that this ZT is important is it feeds directly into the efficiency. So this is showing the efficiency here on the y-axis as a function of the hot side temperature on the x-axis as a function, or for, I should say, different values of Z. So these are Z now as opposed to ZT. Bismuth telluride with a ZT of about 1.3 at 400 Kelvin. That puts it between this, somewhere between this 002 and 003 line, but of course we're down at 400 Kelvin. So it means that typically we're talking of an efficiency of only 2 or 3% in most applications. Perhaps more serious from the point of view of usage across a wide spectrum of temperature is that the performance falls off quite significantly at higher temperatures. And for that reason, we really, I would say, we need a portfolio of materials that cover the applications in the different temperature regions. So we've got down at the one end here, we've got things like sensors for medical devices that maybe run off body heat, all the way through things like automotive and the aerospace, which are at the higher end of the temperature range. And if we look at the performance of materials, so this figure on the top left here is actually a chart that my good friend and colleague Bob Freer at Manchester has produced for a forthcoming compilation of data. And it's not important really what each of these compounds is. The main point I wanted to try to illustrate from this figure is that different materials show their maximum values of ZT at different temperatures. So for instance, 1A here is the bismuth telluride, and you can see as we go to higher temperatures, it falls off quite sharply in performance. Its peak performance is around about 400 Kelvin. Whereas something like lead telluride, which is this one, for instance, shows its higher performance at much higher temperatures into this sort of high T region. And similarly, we have other materials, for instance, boron carbide here, which is the one in black, number 12, that keeps on going up and will just keep on going up for quite some way beyond 1200 Kelvin. So it's a high temperature material. So we really need to be able to design materials towards the temperature appropriate to specific applications. A further constraint that we have is really on the actual component elements themselves. So most high-performance thermoelectrics to date, including bismuth telluride, have appreciable quantities of tellurium in them. So bismuth telluride down at ambient type temperatures, lead telluride at higher temperatures. The abundance of tellurium in the Earth's crust is about 1 part per billion, which is about the same as gold, for instance. So what we really want to be doing, this is the periodic table shown here on a logarithmic scale where the height of each of these tower blocks is proportional to the abundance of that element in the Earth's crust. And you can see tellurium is really down on the floor there, whereas really we'd like to be using some of these much more abundant elements, maybe sulfur, silicon, the transition metals, in order to get something where we can make large amounts of material that perform well at the temperature appropriate to a given application. So how do we overcome that fundamental problem of having three intrinsic properties of a material that contribute to ZT, but they're interdependent on each other? Well, there are a number of design strategies that as people have studied more and more thermoelectric materials, they come up with a range of design strategies. I'll speak about some of these in today's presentation. So for instance, the phonon glass electron crystal has been quite a popular way of achieving high performance, because what it does is introduces cations into cavities which are really too large for that cation, and as a result that cation shows localized vibrational modes. It's termed a rattler. They're often referred to as rattling modes, and those rattling modes can interfere with the phonon propagation, so it's affecting that kappa L component of the thermal conductivity without necessarily impeding the electrical transport, which happens through some kind of framework. This is a scudridite, which we'll be seeing later. Another way of influencing that thermal conductivity is essentially by creating interfaces, and that can be done by introducing what are called nano-inclusions into some matrix. So there's a series of materials Mercury Canetsidis developed called the last phases. They've got nano-inclusions within what is essentially a lead telluride matrix, or indeed introducing a second phase into that matrix, and then we get phonon scattering at the interfaces between the two phases. It's also possible to do some microstructural engineering. This is something I won't be speaking about today, but you can do grain boundary engineering to effectively scatter phonons selectively compared to scattering electrons. Phonons typically have a longer mean free path than electrons do, so therefore you can actually design your grain boundaries to impede the propagation of phonons without necessarily affecting the electron transport. Resonance states is again one I won't speak about. This is really trying to tune and adjust the band structure itself by introducing fairly deep-lying impurity states to introduce a perturbation into the band structure. So for instance, thallium in lead telluride is a prime example where resonance states give rise to a high thermal conductivity, a high thermoelectric performance. A type of material that I will speak about quite a lot, because we've been doing a fair amount of work on this over the last few years, is what's called a phonon-liquid electron crystal. And this is a material where we have some sort of lattice, underlying lattice, with mobile cations usually within that lattice. And at some critical temperature, those cations, effectively that sublattice, either melts or partially melts, and that then could lead to significant reductions in thermal conductivity. And finally, something that was first proposed by Hickson Dresselhaus, Millie Dresselhaus, probably over 20 years ago now, is that if you decrease the dimensionality of a solid, then you actually introduce more discontinuities into the density of states. And given that the Seebeck coefficient is proportional to the derivative of the density of states at the Fermi level, if you can introduce discontinuities and then fill up to that point with electrons, then it's possible to get enhancements in Seebeck. I think to a certain extent the jury is still out on that one, because I think there are also, when you go to low dimensional systems, you also introduce some interfaces between layers and so on, and that can also affect the thermal conductivity. So this is some work that we've done very recently. So we've not yet even published it on nanocomposites of bismuth telluride. So this is trying to take the kind of current state-of-the-art material at low temperatures and try to improve it. So what we've done is we've done a colloidal processing route where we essentially mix the bismuth telluride with known amounts of graphene oxide. And after some treatment, we do some decomposition of that graphene oxide to reduce graphene oxide. So we introduce essentially a carbonaceous phase that's well distributed throughout our bismuth telluride. And we can follow that process using Raman spectroscopy. So this curve right at the very top here, for instance, is a 1% reduced graphene oxide bismuth telluride composite. And the important thing to note really is that this carbon, what's called the 2D peak, which is present in graphite, is not present in the composite. And also this carbon G peak, which is very sharp in graphite, is broadened considerably. And also you'll notice the intensity ratios of these two peaks have swapped around. So all of those factors together suggest that we don't actually have graphite there. We don't really have graphene there either, as far as we can tell, but we probably have few layer graphite-like sheets. So it's somewhere between bulk graphite and single layer graphene. And what that achieved is it allows us to have significant reductions in the thermal conductivity. So I mentioned the anisotropy of bismuth telluride. So these are measurements made parallel to the pressing direction and perpendicular to the pressing direction. But you can see that in both cases, as we add some reduced graphene oxide into our material, we get quite significant reductions in thermal conductivity in both cases, and in fact up to about 30% of reduction. And we find that the optimum contents around about, for the thermal conductivity at least, depending on which direction we're measuring, either 0.25 or 0.5 weight%. And what that does is it increases our figure of merit. So although we get a slight degradation of the electrical properties when we make the composite, that's offset by those quite substantial decreases in thermal conductivity. And we end up increasing ZT by about 20%. So at our sort of maximum ZTs here, this is the perpendicular orientation, we can get up to about 1.6, for instance. What's also interesting, though, is that we can actually improve the performance even of the pristine phase that doesn't include the carbon. And we think that that's because essentially by putting it through this colloidal process and the ultrasound, we actually reduce the grain size quite significantly, and that can contribute to reduced thermal conductivity and consequently higher thermoelectric performance. Now, I mentioned as an alternative to compositing that there's a class of materials called phonon glass electron crystal materials. So this is some work that our chairman this afternoon actually carried out whilst he was at Reading. This is some filled skutterudite. So here's the skutterudite structure. It's essentially the ReO3 type structure, and in its normal form, something like cobalt antimonide quite a high thermal conductivity. It has no cations in these cavities. It's just that octahedral-based framework. If we introduce some rare earth cations into that cavity space, we have to adjust the electron count of the host as well. So we have to replace quite a lot of the cobalt with iron in order to maintain the appropriate electron count, because this is, of course, donating 3 electrons when it goes into that cavity. We can reduce that thermal conductivity by about a factor of 8 or so. And that can give rise to quite significant performance enhancements. So what our interest was really was thinking about, well, if a single rare earth cation with the localized vibrational modes can cause significant reductions in thermal conductivity, what happens if we were to use multiple fillers? Because as we can see here, different fillers have different vibrational or resonance frequencies, and therefore they're going to interfere with different parts of the phonon spectrum. So that was our motivation, and also because we were working on a project that was related to energy recovery and exhaust systems, we wanted to be able to scale up. So we started looking at mechanochemical alloying to make these materials. So that allows us to make batches significantly larger than traditional sealed tube synthesis. It also, as we can see for the electron microscopy here, it gives us, here are mechanically alloyed materials, here are materials synthesized conventionally by high temperature methods. It gives us both a smaller grain size and a narrower grain size distribution. So the grain size is quite significantly smaller than it is in the material from high temperature synthesis. So in terms of the single versus the double filling, what we can see here is that on these plots is the thermal conductivity, which is the key thing that we're really targeting. We can see that the triangles are the conventional materials, and the circles are the the triangles are the single-filled materials, the circle are the double-filled materials, and then for each we've got both the conventional and the ball milling. So the first thing to notice is actually the preparation by ball milling it gives us a slightly improved, or in other words, lower thermal conductivity, and also that the double filling is giving us a lower thermal conductivity than if we had single filling. So that was what we set out to achieve, and that's then reflected in the ZT values here, because we can see, unfortunately, we've now changed our symbols. So now the double filled are the triangles, and we can see that the performance of the triangles, whether made by conventional processes or by ball milling, is significantly improved over that of the single filled materials, and we get a maximum ZT of about 0.93 at 823 Kelvin. So that seemed to sort of vindicate the strategy of saying, well, what happens if we use more than one filler, and we aim to introduce ions, rattlers with different vibrational frequencies? It does indeed give improved performance. So we then started thinking about module construction. So we'd previously collaborated with Gao Min at the University of Cardiff on single-filled scuderites, where the N and P type were both single-filled. So this is one of the modules that they produced from our materials. This is a 9-couple array. And what's referred to in this diagram as the Cardiff module, you can see actually gives about 3.5 watts per cubic centimeter. So in other words, if we compare that with the one in pink here, which is a commercial bismuth telluride module, you can see that what we're really getting is we're getting bismuth telluride performance, but now at somewhat higher temperatures, and we get a maximum power output of about 0.16 watts from this module at 365 degrees C. So having made the doubly filled materials, of course, we then wanted to see what they performed as in a module. So here where the N and the P type are both doubly filled, and we can see that the output power now is in watts, so it's not directly comparable with what's on the figure on the bottom there. But if I put the data from the bottom and I put it onto the same scale, the maximum performance that we have in the singly filled scuderites is where that star is. So what we can see is we've significantly improved from round about 0.2 here watts. We've improved that. So up to something around the same temperature, at least around the 1 watt. And if we go to slightly higher temperatures, we managed to get a maximum power out of this of 1.8 watts. So again, that improved performance in the materials feeds through into an improved performance in the module itself, and we end up with something that gives us at the highest temperatures, our maximum efficiency comes out as about 4.5% efficiency. So we went on from that and started thinking about, well, if we're going to use these, we need to be able to scale them. And this is where the ball milling became important, because we started preparing batches in 60-gram batches. That allowed us, or I say us, allowed our collaborators at University of Cardiff to produce batches of modules, 12 modules out of a 60-gram batch of N and a 60-gram P type material. They also developed a high throughput screening technique to check these modules rapidly, because module construction is a major technological challenge in its own right. And they found that actually across the batch of 12 modules, the internal resistance was about 101 milliohms, but only varied by plus or minus 1 across the batches. Now, despite the fact we get materials with high ZTs, so here are the materials that went into these high volume power density modules, we're at ZTs of about 1.1 to 1.2 maximum. The module ZT at 300 Kelvin, so down here, is only about 0.12, whereas the materials themselves are maybe about 0.2, just above. So we lose a lot of performance in fabricating the module due to contact issues and so on. But nonetheless, we do get something that's about 4% efficient at a delta T of 362 Kelvin. And that then gives us something. It produces about 17 watts per cubic centimeter. And these were then tested. For instance, this is a Ford 2-liter engine. These modules were tested on that engine in terms of the extracting the waste heat and converting it into electricity. And this generates about 500 watts, about between 400 and 500 watts. So we can actually start to use materials in real applications. In terms of the rest of the talk, I'm really going to focus on sulfides. And what I'd like to do is just very briefly say why sulfides have attractive features. Many of them, including TiS2 that's shown here, are low dimensional, so that gives them a very highly structured density of states. The metal-sulfur interaction is quite covalent, so that means that we're going to get broader bands and higher carrier mobilities. It's also very polarizable as an anion matrix, so that means that we're going to see significant cation mobility and potential for non-liquid electron crystal behavior. Sulfur is also incredibly abundant, so that point I made earlier about the abundance of the materials becomes really quite important. And we were really struck by the fact that if you take TiS2, these are some data from the literature, you find that electrically TiS2 is actually quite good. It's performing in quite a comparable way to bismuth telluride. What kills it is the thermal conductivity. So at 300 K, ZT drops from about 0.86 down by about a factor of almost 5, and that's predominantly because of the thermal conductivity. And the other point really that attracted us about sulfides is that because of the sort of temperature range in which they're stable and they show high performance and so on, they're well suited to industrial waste heat. And some estimates of industrial waste heat indicate that about 80% of it is actually released in this temperature range over about 373 to 535 Kelvin. That's just a very good range for sulfides because sulfides are not especially stable at higher temperatures. So our first foray really into sulfide thermoelectrics was what are called shandite, based on the shandite mineral. It's a half metal. It's unusual that it has a very large Seebeck for such a low resistivity. So at 350 Kelvin, its Seebeck approaches minus 60 microvolts per Kelvin, and yet the resistivity is still less than 0.3 milliohm centimeters. So it's quite an unusual combination. It also has the attractive feature that although not low dimensional, it's pseudo low dimensional. So we have these Kagome-like layers here, these network Kagome network type layers of cobalt and tin. The blue are the cobalt. So every CO3 triangle is then capped either above or below with a sulfur atom like that. Then the layers are joined together with a second tin atom, which is in a trigonal antiprismatic site. So we get this sort of pillared layer structure. So although not a true layered structure, it has low dimensional character. And what that means is we have a highly structured density of states, as we can see here. These are some band structure calculations from the literature. Our collaborators at Reading have also done some spin and polarized calculations, which confirm that it is a half metal. But the important point is in the region of the Fermi level, what we have is we have two bands, the upper of which is partially filled in the stoichiometric end member. So what we've been looking at is can we lower that Fermi level through this region here of a highly structured density of states and increase the Seebeck coefficient and improve the thermoelectric properties. And in fact, we can go, if we use something like indium, for instance, which each time we put an indium in, it removes an electron, we can go from a 47 electron material to a 45 electron material. And at the midpoint where we have a 50-50 tin-indium mixture, it's a semiconductor because the upper band is empty, the lower band is filled. And then if we go further, we start depopulating this lower band again. So rather than showing all of the properties, I thought I'd just summarize really what's happening as we replace tin with indium here. What we find is that our Seebeck starts to increase as we move towards a more semiconducting region where the upper band is empty and the lower band is filled. Our resistivity also increases. And in fact, when we get to that 50-50 mixture of tin and indium, we do see at that point and just beyond, we do see semiconducting behavior, and then we come back out the other side and it becomes metallic. So this is quite an unusual example of a metal to semiconductor to metal double transition as a result of chemical compositional changes. When we get to that second metallic region, the Seebeck coefficient never really recovers. It doesn't get the values that we get before that halfway point, and as a result, the power factors beyond that 50-50 composition tend to be quite miserable compared to those before that 50-50, and we can see that graphically here at 2 temperatures. It sort of falls off a cliff edge as we get to that 50-50 composition. Our thermal conductivity doesn't really change very much in terms of the lattice contribution, and that's not surprising because the mass of tin and indium are almost the same. They're right next to each other in a periodic table, but we do get a broad minimum in the thermal conductivity as we approach that 50-50 mixture. The 50-50 is at the lowest point here. We get a broad minimum due to the fact that we get the electronic contribution shows a minimum at that point because, of course, that's where the resistivity is highest. So the net result of that is we get quite promising figures of merit before we get to that 50-50 composition. We're reaching 0.3 at our maximum point here, and that's at about 675 Kelvin. But as we get closer to that 50-50 composition, they start to decrease, and then it falls off a cliff edge, and we get very low figures of merit in that second metallic region. So another way that we can tune those properties of adding and removing electrons is actually to focus on the A site cation, so that's the cobalt cation, and replace it with either iron, which removes some electrons, or nickel, which will add them. If we use nickel, we find that actually all that happens is that we add more and more electrons to that upper band, and the material becomes increasingly metallic, and the thermoelectric properties really fall off quite dramatically. Whereas if we do iron, we see a fairly limited range of solid solutions, so only up to about 0.6 ions, and we degrade the electrical properties, which is the resistivity and the Seebeck coefficient. So we see this resistivity rises, the Seebeck rises as well, coming down. It becomes more negative in this sense. But the important point is that the increase in the value of the Seebeck outweighs the increase in the resistivity, and consequently we find that we increase our power factor. And therefore, what we find is we actually get ZTs, which are slightly improved, maybe not quite as much as they are when we tinker with the B site cation, the tin cation, but nonetheless, we can achieve a similar result by adjusting the electron count through the transition metal cations. And then, of course, we can combine those two features. We can do substitution of both the transition metal and at the main group cation site. What we find when we do that is that we seem to enhance the two-dimensional character of the material, because what we see is quite a significant increase in the C lattice parameter, for example, and we can push our ZT, our maximum ZT, up to about 0.28, but at a relatively low temperature. This is only 473 Kelvin, so that's quite a good value of the figure of merit at that temperature. Now, we've done quite a lot of combinations of cobalt, iron, tin, indium, but what we find is that the highest ZTs are always at a similar total hole content. So that is when the iron content, which is given by X, and the indium content given by Y add up to 0.9 or thereabouts. So here are three different compositions with three different values of the iron content and the indium content, and you can see the properties are all quite similar. So there's something about that 0.9 hole content that is important. And from our band structure calculations, we find that what we're doing really when we go towards 0.9 is we're moving that Fermi level more and more into a highly structured density of states. So that was really our first foray into sulfide minerals. And since then, we've looked at a range of sulfide minerals. I won't be talking about all of these today. I won't be really talking about tetrahedrite at all, but I'll say something about bornite and also the zinc blende related materials, which are derived from the corner link tetrahedra that are in zinc blende, chalcopyrite and the kestrite stannite pairs in particular. Chalcopyrite is a really quite interesting thermoelectric material because it's a rare example of an N-type material, and it has quite promising electrical transport properties, but very poor thermal conductivity. So its thermal conductivity is similar to an unfilled scutterudite, about 9 watts per meter per Kelvin, and consequently its figure of merit is only about 20 to 30% that of the best P-type sulfides. So what we've been doing in a very recent project, and this is going on at the moment, in fact, some of this work was presented at the VCT conference this morning, for example. We're trying to optimize the carrier concentrations through substitution either at the copper site or at the iron site in chalcopyrite, and combining that with grain size reduction using high energy ball milling, and also trying to use the microstructure to control the thermal conductivity. So I'll just choose one example from this system, which is the copper chromium system, where we've substituted copper with chromium. And what we find is that if we do that, we improve the resistivity. So the resistivity falls quite dramatically. And also, surprisingly, we actually we don't impede the Seebeck coefficient as much as we might have expected for this reduction in resistivity. So although the Seebeck coefficient does indeed get smaller in absolute terms, it's not as much a reduction as we might have expected, and therefore we almost double our power factor compared to the end member phase. However, the fly in the ointment is that we find if we take the Seebeck and resistivity at a given temperature, and we're choosing 673 here, we see that they vary in a non-systematic way with chromium content. We might have expected them to vary steadily as we increase the amount of chromium, but instead of that, they follow this sort of double zigzag type curve, and that mirrors the carrier concentration, or the changes in carrier concentration. So that really led us with our colleagues at Manchester as part of the project to look at the electron microscopy. And what we find is we find inclusions within these materials. This is just one composition here. This is 4% chromium. We find inclusions over quite a wide range of length scales, from the sub-micron level up to quite large inclusions like this one, which are almost 100 microns. And we found that actually the EDAX, or the energy dispersive X-ray data from the microscope, actually tells us that whilst the major phase is consistent with a chromium-doped chalcopyrite, these inclusions, this secondary phase, for instance, is a chromium-rich secondary phase, and we think that is what is affecting the carrier concentration in a non-systematic way, because it will depend on things like thermal history in terms of the formation of those inclusions, and we think that that is actually what's causing that apparently random variation in properties of the electrical transport properties. However, these inclusions seem to have a very beneficial effect on thermal transport because they act as phonon scattering centers, and they reduce the lattice contribution of the thermal conductivity. So that's this curve, set of curves here. This is the lattice contribution, this is the electronic contribution, this is the total thermal conductivity, reduces the lattice contribution to thermal conductivity by about 35% at 673 Kelvin. And that actually allows us to increase our figure of merit by a factor of almost 3 compared to the end member copper iron sulfide. And we can get up to, at the moment, 0.31 at 673 Kelvin. So moving on from chalcopyrite, if we introduce not just 2 cations into the zinc blende structure, but we introduce 3, there are 2 principal possibilities, the kestrite and the stannite structure, which differ only in the way that the ions are ordered. So for instance, if this was an A site with copper in it, and the orange ones here are copper, in the kestrite structure, the copper are in every metal layer. In the stannite structure, they're restricted to 2 out of the 4 layers. These are very difficult to distinguish by X-ray diffraction, and there's a lot of confusion in the literature, and we've written a whole paper on identifying which are the stable phases for different compositions. I won't go into that lengthy story now, but just to say that a combination of neutron diffraction and DFT shows that it's the kestrite structure. When A is copper, it's partially ordered, and when A is silver, it's fully ordered. And the main reason for our interest in these, as I said, the chalcopyrite itself has got a thermal conductivity of about 9 watts per meter per Kelvin. That of the kestrite stannite type materials is about 1/3 of that at 3 watts per meter per Kelvin. Now, kestrite end member itself has a slightly odd property, which I'll come back to, hopefully, if I've got time towards the end, in terms of a phonoliquid electron crystal. It appears to show in this region here what has been referred to as a semiconductor to metal transition on heating. So here's the resistivity, clearly semiconducting behavior, and then it turns around and starts to increase. So the Seebeck show anomalies as well. And also we find that DSC data show quite significant changes in slope in that region, which maybe show up more clearly if we take the derivative of the heat flow. But nonetheless, we have something going on in that region where we have quite marked changes in electrical properties. Now, as I say, this has been described as a semiconductor to metal transition. I think it's unlikely to be a true metal, because this is quite a high Seebeck coefficient of about 230 microvolts per Kelvin. And it's also quite a high resistivity of about maybe 15 milliohm centimeters to be a conventional metal. So our belief is that it's actually a transition from an activated semiconductor to a degenerate semiconductor. But to study this, we took this, Jesus mentioned about the ISIS neutron facility. We took this to the Polaris, which is an instrument within this aircraft hangar type facility here, which is one of the Target Station 1 instruments. Polaris is a multi-bank instrument. So this is just one bank from Polaris as a function of temperature. And as you can see, surprisingly, there's very little variation in the neutron diffraction patterns as we heat this up. And if we actually do the Rietveld refinement, we find that when we get through this region, this gray stripe showing the region where those electronic anomalies are, we see no lattice parameter anomaly either. Now, fortunately, the student, PhD student who was doing this, whilst initially disappointed, decided to look at this in a bit more detail. And what he found is actually, if we look at the site occupancy factors, initially we have this disorder between the copper and the zinc sites. So it's not a 50-50. It's a slight preference for the copper in one site, in the 2C site, than the other site, the 2D site. And then there's a copper that fully occupies this 2A site. So this is our room temperature structure. But when we heat it up, it appears to get to an order-disorder transition where these copper and zinc cations become fully disordered. So that would be this dotted line here. This would be 0.5 site occupancy factors in each. But at the same time, the actual total occupancy of that site falls away. And also, the occupancy of this site that was fully occupied by copper starts to fall off. So what we find is that the copper-zinc disorder is accompanied by a delocalization of a fraction of the copper ions. And in fact, by the time we get up to our highest temperature of 973 Kelvin, we find that the crystallographic formula it involves about a 30% deficiency of copper within that formula. And when we do a difference Fourier map, we see that that copper is actually distributed over a whole range of interstitial sites in this structure. So it looks as if that copper sublattice is starting to melt. So it looks like phonon-liquid electron crystal type behavior. And that's associated then with this change from an activated semiconductor to a degenerate semiconductor. So I realize I'm probably getting close to the end of time, so I'll go through some of the remaining material in a reasonable speed. We've done some hole doping on that end member phase. We get a single phase region up to about X of 0.15. So in other words, what we're doing is replacing germanium-4 with some copper. That requires the copper to be oxidized from copper plus to copper 2 plus, and consequently we introduce some holes into our structure. What we see then as we increase that hole concentration, the resistivity falls. And also, of course, then there's a corresponding fall in the Seebeck. And although the phase transition is still evident, you can see that it's gradually being suppressed. And we think that that's because there have been some calculations that suggest that the copper defect formation energy is increased as we make copper-rich phases. So it becomes more difficult for those copper ions to delocalize and for that copper sublattice to melt partially. So we get thermoelectric properties. We get up to, I won't go through these in detail, but again, the power factors are increased as a result of those changes in the transport properties. The thermal conductivity is also increased, principally because of the changes in the electrical contribution, which are shown here. But nonetheless, this increase in the power factor is sufficient to increase the ZT slightly, and we get up just about to about 0.2 at 600 Kelvin. So then we thought, well, what happens if we replace that zinc with a magnetic ion? Because there's been some studies which suggest that if you have a magnetic ion there, the effective mass of the carriers due to coupling between the electron and the magnetic moment, those effective masses increase, and that can actually be beneficial for the Seebeck coefficient. So we took this end member phase, and we essentially tried to do the same process with it, replace the germanium-4 with some copper, which causes the copper to oxidize to copper 2 and introduce more holes and hopefully improve the transport properties. There's one slight fly in the ointment with this phase, and we still don't fully understand this yet. If we do the measurements of the resistivity and the Seebeck on cycling, we find that actually the resistivity gradually falls from the first to the second to the third cycle. After the third cycle, it's more or less a constant value, and we see corresponding changes in the Seebeck as well. We're not quite sure why that is yet, because any thermal analysis that we've done suggests that the changes occur at significantly higher temperatures than we're getting to here. But nonetheless, once we've done that doping, the materials become stable with respect to cycling, and they have a significantly lower resistivity. You'll notice there's an axis break here. And although the Seebeck coefficient is reduced, there's a 3 to 5-fold reduction in the resistivity on substitution. And that means that, again, that's sufficient to improve our power factors. We also get a slight increase in thermal conductivity, but not as big a change as the improvement in the power factors. So the net result is that we now get up to a figure of merit that's about 2.5 times that of the unsubstituted phase, and significantly, in view of the fact we were trying to get an improvement as a result of a magnetic ion being here, about 50% higher than that of the zinc analog. So we're up at about 0.3, but I would stress at quite low temperatures, at 200 degrees centigrade. So it's quite useful for industrial waste heat type application. So to finish, I just have a few slides on sort of that phono-liquid electron crystal type behavior. And the archetypal example in many ways are the copper sulfide and copper selenide of this type, which at high temperatures are anti-fluorite type structures. And it's found that the copper ion mobility at high temperatures leads to a melting of the copper sublattice. So effectively, the anion lattice stays the same. The copper sublattice melts, and it assumes a liquid-like state. And that impacts substantially on the thermal conductivity and reduces the thermal conductivity quite markedly. And ZT maximum reaches about 1.6. However, ironically, it's that ion migration that leads to these materials degrading in use, because if they're subjected to a temperature gradient and have liquid mobile copper ions, and there's also a potential difference being generated, you'll get copper ion migration, and it's seen that copper starts to plate out on one face of the thermal elements under a sustained operation. And of course, then the performance degrades. So what we wanted to do is we wanted to try to stop that migration. So we looked at this material bornite, which is a high temperature phase, is also anti-fluorite related. The difference now, this would be the end member here without any copper deficiency would be M8S4. This is M6S4. So that means there are 2 vacancies per formula unit. And those are distributed at a high temperature. The vacancies, the copper and the ions are distributed randomly over tetrahedral sites in the anti-fluorite type structure at high temperatures. It has a low thermal conductivity, and in principle, we think that the ion cations are going to suppress that copper ion migration, but unfortunately, the electronic properties are low, and we get a ZT of only 0.4. So we're going to look at chemical substitution to increase the power factor without impacting on that low thermal conductivity. So I'm going to go through this fairly quickly. We've done 2 different things here. We've used copper deficiency, so we've made some copper vacancies. So again, a similar strategy that has to oxidize some of the remaining copper to maintain charge balance. It introduces some additional holes. We do get some significant improvement in the electrical properties. The power factor is more than doubled. The thermal conductivity is also slightly reduced, but the main impact is on the electrical properties, which is what we were targeting. And we can get the ZT that exceeds 0.6 in that material. We can get similar performance on a similar basis by just tuning that copper to iron ratio, which again results in oxidation of some of the copper. And once again, we can get to ZT of about 0.6. So the final example I'll show is where we sort of combined 2 strategies, is that we wanted to adjust the copper to iron ratio whilst also having some vacancies present. So this is no longer copper 5, this is copper 4.94. So we introduce some vacancies, we then adjust the copper to iron ratio. So once again, we see significant improvements in the electrical resistivity, which falls, which then feeds into quite large increases in power factors. Power factors are more than doubled here. And then we look at the thermal conductivity. We find that it does increase, but we're not impacting on the thermal conductivity quite as much as we were in those other series. And I think that's probably because of the vacancies. And we reach a ZT maximum that's almost 0.8, 0.79 at a very low temperature of 550 Kelvin. So this is actually one of the best performing materials in this industrial waste heat region. Interestingly, the electrical properties and the Seebeck coefficients, regardless of which series we take, so these are the 3 different series I've just mentioned, they seem to follow a common curve. And in fact, the power factor seems to scale almost linearly with the copper-2 content. So as I say, each time we're doing these changes, we're trying to modify the copper-2 content to introduce some more holes. We see that we increase the power factor in an almost linear fashion with the copper-2 content. However, to get the maximum performance, this is where we get the highest ZTs here, it's important that we don't just have the optimized copper-2 content, which is about 2 to 3%, but we also need those additional vacancies. And then finally, that reproducibility issue, we seem to have cured that as well, because if we do 8 runs here, we find that there's virtually no change from one run to the next. So it appears that the strategy of introducing some iron into the anti-fluorite structure has actually succeeded in terms of avoiding some of that degradation. So this just shows where some of those materials sit. I'm not going to spend a lot of time on this. I'd like to get to the summary slide in a moment. But just to show that at 550 Kelvin, bornite is probably the best material around at the moment, even better than the P-type tetrahedrites, which have been much more studied. But you'll notice that down here, we're really struggling to get comparable performance out of N-type materials, the ones that have that green box there. So in summary, I hope I've shown that there's a range of alternatives to bismuth telluride, which contain earth-abundant elements. We do have a number of materials design strategies, some of which I've discussed today. But there are challenges. Achieving comparable performance in both N and P type materials is an issue for materials such as sulfides. So here's a graph, for instance, of a review I wrote fairly recently. All of the solid points here are P-type materials. The open points, which are down here, are N-type materials. So there's a long way to go to get compatible N-type materials with similar performance to the P-type. Material stability is also an issue, and that applies to any of these materials I've mentioned. Scuderidites, for instance, show volatilization. Sulfur can volatilize from sulfides either during processing or operation. Ion migration, as we've seen with the phonoliquid electron crystals, can also impose limits on how these materials are used. And then the whole issue of device performance, and this is not something we've done ourselves, this is something we've done in collaboration with the University of Cardiff. Device performance is a whole new issue on its own, and I think it's a whole series of research projects once a material's been developed. So finally, just to acknowledge, I won't go through them one by one, but the people at the University of Reading who've done this work, a combination of postdocs and some PhD students who are now completed, people like Sebastian Long, and the people who funded this work, and then our collaborators at other institutions. And I'll just leave you with a very quick advert for anyone whose interest has been sparked in thermoelectrics. There will be an RSC volume coming out towards the end of this year in their inorganic materials series on inorganic thermoelectric materials. And finally, I'd just like to thank you for your attention.
So thank you so much, Professor Powell, for such a nice talk. I can see that so far there's no questions, so I hope that the people attending can make questions. But in the meantime, I'd like to ask myself. So because you said that when creating a thermoelectric module, there are some electrical loss because of the contacts of the materials, of the pieces in the module. How could this be solved or improved?
You have to be very careful. It's quite an involved, a complicated device. It looks quite simple because it's just a block with N and P type materials. But on those M and P type materials, there are diffusion barrier layers to stop ions migrating. There are electrical contacts, there are solders, there's then a ceramic layer. It all has to be joined together, and the key thing seems to be those electrical contacts, and it's about finding the right solder that forms a mechanically stable bond to the surface of the thermoelement, whilst also maintaining a good electrical contact. And where we've struggled with the scuderidites is actually finding a solder that actually operates at the high temperatures where we'd want to use a module. So although we've got quite good performance, the performance, if we went up another 200 degrees, would probably be even better. But unfortunately, our solder melts by the time we get to that point. And it's a question of finding the right solder in order to get both good mechanical contact and good electrical contact.
Thank you. I have one more question. How easy is it to prepare composites of bismuth, telluride, and graphene oxide? Do you manage to obtain a homogeneous mixture?
Yes, we do. I didn't show it on the interest of time, but as well as those individual Raman spectra that I showed, we've also done Raman mapping of the surface of the composite. So we make the composite, we press a pellet, we then map the surface with Raman spectroscopy, which shows up the different carbonaceous regions, and those regions are actually very evenly distributed. I think it's because we're going down to that colloidal level when we do the mixing that we can get good homogeneous mixing there.
Okay, I have one more comment. Thank you so much for your speech. My question is, you have mentioned that it is possible to scale up the synthesis of scuderidites by ball milling. Sorry, how many can be prepared?
We were preparing on what for us was a large scale. When we work on sealed tubes, for instance, we work on 3 to 5 grams. So when we went up to 60 grams, that was quite a big leap for us. We have looked at going further, and I think with kind of laboratory-sized ball mills, you can get up to maybe 80 to 100 grams. But I know that I've been in discussion with Peter Balash in the Czech Republic, I think he is. I always get confused, I'm afraid. And he's got sort of more industrial scale mills, and he's producing materials on the hundreds of gram scale by ball milling. So ball milling, if it works, it's a very scalable method.
Okay, so I'm not sure if there's any more questions. So if it's not the case, maybe we should move on to the next speaker.
So